Hello, wonderful people. Wow, it's echoing here. Wonderful to see you here. I think my last Euruko was completely remote. Remember, there used to be COVID and all that stuff, so great to see you in person. A wonderful city, loving the views, the mountains, everything, just excellent, excellent. My name is Julik. I've been coding in Ruby for about 20 years now, maybe more, and working professionally with it for maybe 12 years, 13, never mind. And I wanted to talk to you about the virtues of slot scheduling and what the GCD method is for. Maybe you have used it, maybe not, but you might discover it. And I wanted to make a quick break. I know there are members of the Ukrainian community listening in. I know that the Ukrainian Ruby community is very vibrant. I love to visit Kiev. I spoke for Ruby Motion, I think, once. And I just wanted to say, let's not forget, there is a war going on in Europe. It's an unjust war. Ukraine must be free. The war must end. These links too are two charities that I know are doing great work to help Ukrainians. If you can, help them. I know that lots of people from Russia do not speak on the topic openly for fear of repression. I try to stand up for them. Freedom to Ukraine. Now, on the virtues of slot scheduling. So, for people who don't want to sit here for too long, I have a TLDR of the talk all packaged in one slide. You can make a picture of it and walk away and have conversations in the hall or whatever. Like, this is the super rapid thing. Now we go for the slow version. So I work at a company called Cheddar. We are a fledgling startup in the UK. We're a fintech, and what we do, we help you manage your personal spend. We help you manage your personal finances. We also do peer-to-peer payments on the UK market. If you are a UK resident or you have a UK bank account, you might want to try out Cheddar. It's real neat. And Cheddar is a mobile application. Funnily enough, it is actually a Rails application with a Flutter front end. That's also something that exists. And one of the things that Cheddar does is we integrate with a ton of banks. We call to banks, we get permission from users to access the user's transactions, then we go out to banks, we download the transactions to analyze them, and we show you your spend, some predictions, and we're also able to pay you out cashback automatically. That's also a feature that we support. And all of these bank integrations, and we integrate with 23 banks just in the UK at the moment, which is a huge number. Actually, all of that happens from our Rails monolith. It's all less tech, single app, very kind of bare bones approach, Postgres for everything. And we are unique in a way that, in the sense that we actually do those banking integrations ourselves. Now, people who are in the fintech space, I already spoke to a couple in the hallways. They highlight that when you need to get access to banks, it's always difficult. You have different APIs to contend with. Authentication is hard. Security is hard. Things difficult. However, we chose to do this integration ourselves, which gives us certain benefits. And when we do this transaction syncing, we call out to a bank on your behalf, your user behalf, and the banks return us the transaction information. Pretty simple, except sometimes it's very slow. Sometimes certain banks are down. Also, you need to study at least 20 different ways to mess up OpenAuth and OpenAuth 2. Probably there is a book to be written there about it. But the most important part is that banks update data for people, not instantly, but usually once a day or twice a day. And once this data is updated at the bank, we want to get at it, preferably quickly. Now, our way of getting us this data quickly was initially this. So we would look for people who haven't had their stuff updated in a while. We would query for those, and then we would schedule some kind of synchronization task for them. And we would run this task multiple times a day, depending on the day of the week, etc., etc. And that would be pretty miserable because doing it this way means that you will have very large spikes in your queue depth. So you will queue a huge number of tasks. Your systems will react. If you use auto-scaling, the more jobs you have, the more nodes you are going to spin up, the more money you're going to pay. it's uneven load, which is just an issue that you will be dealing with. And the job that was dealing with it looked somewhat like this. We use job iteration from Shopify. Probably some folks know about it. And that's basically how it would proceed. So it's a way to destroy your application. Like nobody can be as good at DDoSing your application as yourself. So you will inject a ton of jobs into the queue. You will select the jobs. And when you select the jobs, you query the database because just use Postgres, right? When you query the database, your CPU load grows, queue depth increases. The autoscaler says, oh, queue depth is large. We have a lot of jobs. More computers. What do more computers do? Well, they, of course, hammer on the same table. They cause more load on the CPU. They cause more congestion. And then you end up seeing a load pattern on your database which looks like this, which doesn't make you happy at all. It's like there is no issue running a pretty successful Rails app, I would say, maybe on a cluster of Raspberry Pis, as long as you have a good database server. Because that's the thing that will hurt first. So we were thinking, okay, how do we spread this load in such a way that we don't destroy ourselves every day, right? And then this article sprang to mind. If you don't know about this article, I suggest you give it a look. It's old and it's good. It says that simulate anything that involves more than one probability, probabilities over time, or queues. Now we have probabilities over time because banks fail intermittently, and we have queues, exactly the thing. So we thought like, okay, what if we were to model a situation with lots of jobs, right? We would go something like this. We would create a fake job. We would say that this job takes a certain amount of time to complete. We would mark the start time of the job. We would register when the job is supposed to finish, right? And then we would let this job produce some fake side effects. In our case, it would be job spooling more jobs, right? And then, but for example, produce side effects. One of the things that you can do for a job, that fake job that produces side effects, you can say this job causes n unit of load on your fake non-existent model database, right? And then we would run it from a simulator which looks kind of like so. That is a concept related to discrete event simulation, but not quite. This is actually an incremental time progression. So we initialize our simulator and we give it the current time. It's kind of like a game engine. And then every time we increment the time, we check whether any of our jobs have completed. If they did, we take more jobs from the queue, and we record metrics. Now, the important part here is that you want to know how long your jobs take. And just a number is obviously not very nice and not very useful, but we use an APM. And an APM will usually give you some kind of percentiles for how long your jobs take. In our case, it is AppSignal, been using it for a long time and very happy with it. And it gives us something like this, right? So it gives us the mean and gives us the 19th percentile. By the way, the 13.37 seconds, this is calling out to slow OAuth servers at banks. This is not because Ruby is slow, it's because you sit and wait, right? Now, then the question comes, if we have percentiles, there should be a way to actually generate fake job durations based on that percentile, right? But here's the problem. I haven't studied computer science. I haven't studied math. I've done art school. And I've even worked for a CTO who has done art school. Ask me anything, right? So if we have a hunch that there must be an algorithm to do X, but we don't have it, what do? Well, we go to ChatGPT and we ask it a question. Now, I'm not necessarily scared of LLMs as replacing us developers. I tend to see LLMs as a drunken pub companion. You can ask it stupid questions and they hallucinate you some kind of idea, and it might just be inspirational. You know, you should never take it at face value. You should not take it as a truth, but it might hallucinate you something which will make you think, oh, maybe that could work. So after some discussion with the drunken pub companion, we come at an algorithm which is called inverse transform sampling, which is apparently used in games. Go figure, right? And having put an inconspicuous comment that this is hallucinated math and I don't know what I'm doing, this is dog, we get a way to generate values for our jobs, which are going to look pretty much like the real thing. And then from there, for example, we can do a thing like this, right? We run our simulation where we make it use those sample durations which satisfy this sample, which satisfy this distribution. So the job durations are going to match. And then every hour, we dump a huge number of fake jobs into that queue, and we let the simulator run for a number of time. So as far as code goes, this is pretty much all there is to it. Like, I'm not going to explain what is there, but it needs, at the very minimum, it needs some way to record metrics. You need the simulator itself, and you need a sorted heap which is going to simulate your queue, because if you're using a queue which supports priorities, for example, you will want to have fast dequeue operations, and that's just faster to do in Ruby than with SQLite or whatnot. And then we run that simulator, which does something like this. Now, there is an important thing to note here, is that if you go for this monotonic increasing time type of simulation, your unit of work should be somewhat somewhat understandably sized to your tick. Because, for example, if you have jobs which take 200 milliseconds, but the maximum resolution of your simulation is 1 second, you're not going to get very useful output, right? But if your job durations are on the order of 16 seconds, a minute, maybe 2 minutes, then you should be pretty much good to go. So we run that thing. It simulates 1 week of our queue for this type of workload, and then it outputs us things. Now, in our case, it rather looked like this. So we tried different scheduling schemes, and a simulator is just a bit of Ruby code that defines your jobs and the timings. Then you run these, and then it outputs you a very handy SQLite database with all the metrics, because on every tick, you can record what the state your simulation is in, and you can also create metrics like counters and samples from your simulated jobs. And then we just use a hacky thing where we just write to SQLite as fast as possible. This slide is here to nerd snipe Steven Markheim. I don't know if it's going to work or not, but this is basically how you insert stuff into SQLite if you don't care about consistency and you just want to do it as fast as possible. And then having the database, you can query, for example, like this. Now, this thing gives you the information about the number of jobs that have completed at every tick of the simulation. And we entered this exercise with this premise, right? So we want every user account to be synced with a somewhat consistent delay. We want no huge ingress on the queue, because we were using good job, and good job gets way slow and loads the database way hard when you have a lot of jobs lined up. And we want the throughput to be even, because we don't want this autoscaler jumping all the time, right? We want to know, okay, we will need that many machines for that much time, and ideally that should be enough, right? Plus, sometimes we have jobs which may step on each other's toes because they use each other's data, right? Now, how do we go about this? Well, that's how we do it. This is the single, I would say the single most underused class in the Ruby standard library. And the reason it's underrated is because it's not really random. It's actually a memoizing algorithm, and it's called the Mersenne twister. And if you seed it with a value, it will actually give you a predictable deterministic sequence of random values as you trigger it over and over and over again. And this sequence is predetermined. So imagine we want to enqueue jobs for a specific user, or jobs for our entire user base, as a matter of fact, throughout a certain amount of time. We would do it like this, right? Now, we want every user to get a specific kind of delay, and we want this delay to be known in advance, and we don't want it to change. And we want it to be evenly distributed for all the users. Now, how do we do this? Real easy, right? That's all you need to get a delay which is derived from your user ID. And since you are using a random number generator, the values that it outputs, they are going to be pretty uniformly distributed. So you're guaranteed to, even if you have user IDs like 1, 2, 3, 4, 5, still the values that the random number generator will give you, they will have a very nice spread. Now, If, like us, you are stuck with using UUID primary keys, which is a whole different discussion, but anyway, what you can do in there is first you convert your UUID into bytes, which you do using these 25 statements listed here. And then you can convert these bytes into a very, very large integer, and you can seed your Mersenne twister with this very, very large integer. But if we just give every user job a specific start time to spread those jobs out, we still haven't solved the problem of a very large ingress of jobs into the queue. And for that, we figured, okay, what if we don't portion this out? Like, why? And it works like this. Imagine we have our user base. We split it into 8 buckets, which we call slots, right? And then when the time comes to run the jobs for a specific user who is, for example, in bucket 0 or in slot 0, then what we're going to do is we're going to enqueue a blue job, which is that dot at the very beginning, right? And that job, in turn, will spool only the jobs for the users of that slot and no more. Then, when the time rolls over to the next slot, a similar thing is going to happen. We're going to run a scheduling job for that slot, and then it's going to enqueue the jobs for users who land in slot 1, and then slot 2, and slot 3, and slot 4, and so on. Now, the question then becomes, how do we determine how many buckets or how many slots we should have so that it be reasonable? Because we want to have as many as possible, because the more slots you have, the smaller the ingress on your queue is going to be at any given time. And it actually comes down to a very bad coding interview question, which is, I hope, not getting asked at your company. But anyhow, we have a certain cycle duration. For example, we have a cycle duration of 8 hours, and we want to fit our entire user base into 8 hours. How do we determine how many slots to have? Well, if we know that we have a certain number of buckets, in our case, it's the number of possible values of a byte, which I'll get to soon, there is a standard library method for this, which is called greatest common divisor. Do not code it in interviews, okay? And that's exactly what it is for. So it tells us that given n buckets and given this duration in seconds, if we want to get an integer number of slots, that's how many slots we want to have. So our entire workload then becomes 3 workloads, and we execute it in steps. So first, we run the so-called bootstrap job, which knows how long the cycle is going to be. It computes how many slots it's going to use, and it computes when the slots are supposed to start. It enqueues the per slot job, right? And every per slot job which runs then enqueues the sync job for a particular user. And the bootstrapping looks kind of like this, right? And every per slot job we delay just by a duration of a slot, multiplied by which slot it is. So we delay the slot 1 by 1 duration, slot 2 by 2 durations, and so on. And then when we go to execute it, then this is how it works. We select the user accounts for this particular slot, and what we do then is we derive a delay for every user using the same trick, actually, using the primary key of our record in the database to also distribute the users inside of that slot evenly. And then we just enqueue those jobs for that particular user. And that has advantages because, for example, certain queues like SQS will not allow you to look at the jobs before your workers check them out to perform them. Some queues get slower as you have more jobs lined up. And also, specifically for us, queues using databases, they use indexes. Indexes grow, indexes make things slower, and indexes lock. But it gets even more interesting. Now, imagine we have this kind of situation. We have an accept payments job, and it does things with your account, with the monies, right, for which it needs to lock your account. For example, it needs to accept payments, right? But we also have a generate reports job, which also needs to lock your account to perform some calculations and to generate you some reports, like what is your spend over a month, or what is your spend for a week, or what the prediction is, right? Now, how do we use this scheduling method to facilitate these two jobs running together at the same time, right? Now, we started with a line, and that's like a time interval, which is split into multiple intervals. Now, what if we take that interval and we bend it into a donut like so, right? And for example, we know that we place our accept payments job somewhere here, somewhere between slot 0 and slot 1, right? And we know that the generate reports job has to run as far as possible from the accept payments job so that they do not collide for the same account. How do we do it? We trace what we call a reciprocal, and we run the accept payments job for all the blue users, right? All the users who fall into the slot 0. But at the same time, we can run generate reports job for the users who fall into slot 4. And this makes sure that these jobs do not step onto each other, because ideally they will never run at the same time for the same user account, and there will be no lock contention in there, right? Now, if we add another job into the mix, imagine we do some know your customer job, right? Same principle. We can split those jobs to be equidistant from each other, right? And then we run the perform KYC jobs for users in slot 5, generate reports job for people in slot 3, and the accept payment jobs in slot 0. So the next step is to figure out how to select your users for this kind of workflow, because we have, of course, this, and that looks very simple, and it actually is, but it is a Postgres hack, and undercover it actually does this. So that's how you turn your UUIDs in Postgres into bytes, and then what we do is we grab the last byte, which gives us the 256 or 265, don't remember. As many values as there are in a byte, you get the buckets, right? And then we just perform a division, which rounds off, and that's how we can select everyone from our user base who is subjected to this slot. You also want to use the last byte, because if you are smart and you're using UUID v7, your random component is going to be at the end. So that's why the last byte. And where does it get us? Well, this was a desire to get even throughput. And we wanted to ease the load on our systems, and we wanted people we wanted to know that all those things complete to begin with in due time. And boy, did it work. Like the blue graph, that's our throughput on the background jobs. Left part is before we deployed this change. The right one is after we deploy this change, and the spike is when we schedule notifications in bulk. Sometimes these cause spikes, but these are predictable. And this has a ton of advantages, because you will likely pay less for compute, because when you spin up extra autoscaling instances, you spend time for those instances to come up and go down, right? You become very reactive. Your autoscaler can become too aggressive. You need to be very careful with the parameters so that your autoscaler doesn't overscale. If you're using Postgres, you're also got to be very careful with autoscaling because of the number of connections, because if you're not careful, you're going to have PG bouncer and the works, right? Also, it allows you to make estimations, because with this kind of even throughput, you can know, okay, at night, at this time of day, we have throughput of X. How many boxes do we need to satisfy that throughput of X? And one of the things that you can then do, for example, is have pre-committed compute, which you can do in AWS, for instance. You can say, okay, we know that every night we're going to need that many machines of type X with projected growth so-and-so. Like the flat throughput is the ideal situation for most operations. Like for most operational concerns, you want your throughput to be flat. And this kind of scheduling, despite the fact that it's discouraged and stupid, it works very well. There is one thing, however, which I need to address, is that in like any company with a sizable enough user base will get the so-called jumbo users. You know, that's your user who has 10x of everything. They have 10x as many widgets, 10x as many notifications, 10x as many comments. They post 10 times as much data. etc., etc., etc. And this kind of scheduling is not very good for this type of users because their jobs will run longer than your median job. It will throw off your scheduling a little bit, but there are other ways to deal with that. For example, you can locate your jumbo users. Well, first of all, you got to send your jumbo users flowers, usually, because supposedly you're earning a ton of money with them. But also you can locate them on a separate cluster, for example, or you can send their workloads into a separate queue, which will allow you to size your compute for those users specifically. So it's a solvable problem. It's just that they are bigger, right? So stupid solutions work despite folks telling you otherwise. And simulators are fun because we had discussions on the team like, okay, should we try this heuristics for scheduling or that heuristic for scheduling? And in the end, it turned out that writing a simulator, running those scenarios and looking at the metrics that they output told us that, yeah, we can totally do the stupid algorithm and it will totally work and it will be the cheapest solution of all. And also a tiny bit of statistics gets you a long way. Only be careful with hallucinated math, please. And that's it. Thank you very much. If you want to take a look at Cheddar, especially if you are in the UK, you can be our customer. And we also have some nice open source goodies on GitHub. And underneath you can find my blog and Twitter, shitposting a little bit sometimes. Thank you.